All right, so on day 4, we're going to be talking about revolutions around an axis. If you take a 2-dimensional shape and you spin it around an axis, it will create a 3-dimensional solid, right? And this is a super important concept when you get to calculus. You'll learn how to find like the area and volume of solids, which is what we're doing today, but you'll add on to that when you get to calculus. So we're just going to do relatively easy revolutions around an axis. So I've put some illustrations on here. So I'm going to kind of zoom in. So you'll notice on the left, we're starting with a rectangle, right? So imagine basically in like, let's say I have a, let's say pencil, right? Imagine this is a pencil. Here's the eraser, all that good stuff. So imagine I tape a rectangle to a pencil and I spin it around, right? And I start rotating the pencil. Well, what's going to happen is because I'm rotating it, all the edges, the furthest edges away from my axis are going to be spinning around in a circle, and therefore the rectangle is going to turn into a 3-dimensional circular solid, which would turn into a cylinder, which is what we are looking at on the left side, right? And so hopefully you can see, and I will put some graphic videos in Canvas that you can look at if it helps you kind of see a live version of this spinning process. But anytime I take a rectangle and I revolve it around an axis, it is always going to create a cylinder, right? Every single time. Some people mistakenly think that if they take a rectangle and they spin it around, it's going to create a prism. But remember, anytime you spin something around, you're going in a circular path. So the only way we can, anytime we revolve a 2-dimensional figure around an axis, it has to create something circular, right? It doesn't have any chance because you're spinning around an axis like an orbit. So something circular has to be the outcome of that. Okay. All right. So now that I've over-explained that, let's talk about a right triangle. Right. So in this picture, you'll notice my right triangle is attached to the axis by one of the legs that are forming the right angle, because definitely how it's attached makes a big difference. But anyway, this one is attached by the height. And so you can see from the picture on the right that when I start spinning it around, it is clearly going to create a cone. And then the last one is if you start with a basic semicircle or half circle, then it's going to clearly create a sphere when we start rotating it around an axis. Okay? And that's pretty much it, right? Those are the 3 main things that you need to know. Now, which axis we spin it around, right, and how it's attached to the axis could change what our rotated solids look like. So let's go look at a couple of different types of rotating solids. Okay, so if you look at number one is also a right triangle. However, this right triangle is not attached at the height like it was on the previous page. It's being attached here. And so we're going to take this right triangle and we are going to start spinning it around this axis. So I'm hoping you can kind of visually see what's happening here, right? Some people are better at visuals, 3D visuals than others. I'm going to change my color here. So I'm hoping you understand that this corner right here, right, the bottom left-hand corner, it is going to be rotating around. Oh, sorry, I'm going to my pictures are probably not going to be the best here, but I'm going to give it a whirl. Okay, and then I'm going to move this so the center is there. There we go. Right, so this point right here is going to be spinning around the axis, which is going to create this oval shape, right? And this point right here is going to be doing the exact same thing, right? So I'm also going to have an oval with this guy. And then, of course, I'm going to connect this and then draw a line, right? I'm basically drawing his little reflection buddy on the other side. And then I'm hoping you can kind of see what's happening here, right? I actually have a cylinder. Let me shade this in. It's going to take me a really long time to shade that in. I'm not going to do it. So I'm hoping you notice that in this case, we end up with a cylinder, right, with a cone-shaped hole in it. Right? So all of this, right, when I rotate it, all of this is empty space, right? So I have this cylinder with a cone-shaped hole dug out of the middle of it, right? And so that would be my rotated solid, right? So that was a little more complicated because of how the triangle is attached to the axis, okay? So I just want to point that out to you, okay? All right, number two, we're kind of going to do the same thing, right? I have all of these vertices. I'm going to start with this top left corner, right? And he's going to spin around this axis, right? I'm going to let my app here give me a nice pretty oval. There we go. It's pretty centered, right? And then I'm going to do the same thing with all this vertex is going to spin around the axis, and that's what's going to create these boundary points that we have. And then, of course, I can connect this guy and this guy. Actually, let me go from here to here. And voila, there is our 3D solid. So you'll notice we were rotating a trapezoid, but remember at the end of the day, a trapezoid, or this particular trapezoid, is just a rectangle with a triangle on top. So we're basically, by spinning the rectangle and the triangle around at the same time, we end up with a cylinder topped with a cone. So I'm going to write cylinder with an attached cone. Right? So it's like the opposite of the other picture we just did, right? The other one was a cylinder with the cone-shaped hole taken out of it, and this one has that cone attached to the side of it. Okay? All right. The last one we're going to look at here, and then we'll get to some questions. All right, we want to see what happens. I've got a quarter circle, and I want to spin it around this vertical line. Well, I'm going to do the same thing I've been doing. That means this vertex over here, when he starts spinning around the axis, right, he's going to, right, have an oval or a circular orbit there. And then this guy, I'm just going to draw him as, I knew that was going to happen. I'm just going to kind of draw his little reflection arc over here. And voila, this is the three-dimensional solid that we're left with. Right? And this would be a hemisphere or a semisphere, however you want to, right? It's half of a sphere, right? And that's, if I rotate a quarter circle, then I'm going to be, the result will be a hemisphere. Okay, let's go do some actual questions. Let's go. Okay, it says rectangle ABCD with AB 6 and BC 10. Okay, I'm going to stop right there and just sketch what I got. All right, so I've got rectangle A, B, C, D. AB is 6, and BC is 10. Okay. Then it says, right here, it is rotated about side BC. Okay, so that means that side BC is the axis in which our rectangle is going to spin around. Well, we hopefully already know what's going to be created when we spin a rectangle around an axis, right? We are going to end up with a cylinder, right? So I'm going to kind of draw the cylinder. So I'm going to do the same thing I've been doing. I'm going to take my faraway vertices and I'm going to spin them around the axis. Try to get a nice, again, your drawings don't have to be perfect. Luckily, my Notability app gives me nice pretty ovals. And then I'm also going to take my point D and spin him around the BC axis. Go here, let me tighten that a little bit. And then of course I can connect. That's a little off, but that's okay. We're gonna let that go. And voila, there's our cylinder. And then what do we know about this cylinder? Well, it looks like this 6 that we started with, it is now the radius of our circle. So we have here, let me write this down. So we have a cylinder, right? And the information about our cylinder is that it has a radius of 6. And then notice that the original 10 is the height of our cylinder. And there we go. So now we're right back to day one, right? Because now it wants us to calculate the surface area and the volume of the solid that was created by rotating it around the axis. So we're right back, like I said, to our notes from day one where we're doing surface area and volume of a cylinder. So I'm just going to kind of come over here. So remember our surface area formula for a cylinder is 2 pi RH plus 2 pi r squared, right? And we have all that information, right? We've got the r and the h, so we should just be able to plug that stuff in now. So here we go. So 2 pi r h plus 2 pi radius squared. All right, and then let's see, that's going to give us 120 pi for that first term, and then 36 times 2, so we'll get 72 pi for our second term, and it looks like that gives me 192 pi. And our units were inches, so square inches. Voila. And then, of course, our volume formula for a cylinder is pi r squared h, or capital BH, or same thing as a prism. And then pi 6 squared 10. So 36 times 10, so that's going to give us 360 pi, and that would be cubic inches. There we have it. All right, let's go do some more of those. Here we go, number 5. Does the rectangle in the previous example have the same surface area and volume if it's rotated about side AB? Okay. So let's see, I'm going to redraw my triangle that I just had. I'm going to draw it over here in a much smaller form, and you'll see why in a second, right? Because now they want us to rotate it around AB. So here's ABCD. And our measurements were 6 and 10. So I'm just literally redrawing the exact same. Oops, sorry. Here, I'm going to put the 6 here and the 10 here. Okay. So now they want us to rotate it about the AB line, which would be this axis here, right? So now if I spin it around that axis, so now it's going this way, right? We're spinning up and backwards, up and around that AB. So clearly that is not going to give us the same cylinder, right? So, but we want to figure out how does that affect our volume and surface area. So again, I'm going to rotate point D, my vertices that are off of so it's going to be way up here, right? And then same thing with C, right? I'm going to rotate, C goes all the way around the axis. Ooh, that was way off. I can't slide it over. Okay, hold on. I'm going to redo that one. It wouldn't let me fix it. Oh, my goodness. This always happens with ovals. Oh, my gosh. Sorry. It's like I have to draw it in a certain speed or it makes a parallelogram. Seriously? Okay, I'm just going to take it. All right, so then, of course, this is now our cylinder. So it's still a cylinder, right? But now it's like a tall, skinny cylinder instead of the wide, fatter one that we had in the previous one because we went over a different axis. So it's still a cylinder, so I'm going to write that down, cylinder. But now, do you notice on this cylinder, now 10 is our radius, right? And 6 is our height. Right? So clearly no, right? The answer is no. We're not going to get the same surface area. It does say to prove your answer though, so I am going to go ahead and recalculate just to prove, right? So here we go. Surface area. So I'm going to write my formula, 2 pi RH plus 2 pi r squared. All right, I'm going to plug our new numbers in, right? They've been flip-flopped, so that's going to be 10 times 6. Now that's not going to change, but 2 pi r squared, right? That because this is still going to be multiplying the exact same terms together. So the lateral surface area actually isn't changing, but the total surface is because we're changing that radius, which is being squared, right? So this is going to give us 120 pi which notice that was the same thing we got here. So lateral doesn't change, but because our bases are bigger circles, let's see, that gives us what, 200 pi for the area of our bases, whereas up here we only got 72 pi for the area of our bases, right? And what's that going to give us? 320 pi square inches. So definitely bigger because the bases became bigger because our radius increased, okay? And then for volume, same thing, pi r squared h, definitely going to be different because that pi r squared, right now we're squaring the 10 and not the 6, right? So 100 times 6, so now our volume is 600 pi cubic inches, right? That's a big difference, right? Before it was only 360 pi, right? So the axis that we rotate about totally matters, okay? All right, number 6. Equilateral triangle ABC. Okay, I'm just going to draw it. Okay, so A, B, C. With sides 8. Okay. I'm just going to label 1 if that's cool. Is rotated about an altitude. That's different. So I know the altitude of this. I'm going to erase that 8. He's kind of in the way. I'll come back to him. There we go. So now I'm going to draw my altitude, and it's going to spin around the altitude. Well, the cool thing is this is an isosceles, this is an equilateral triangle, so it's perfectly symmetric in all 3 directions, which means A and C are reflection buddies of one another. So as you start spinning it around, right, it's just going to, it's crooked. It's going to bug me, sorry. Right, as we spin A and C around, they're just going to kind of meet up with each other, right? And it's going to create a cone, okay? Now, what we need to figure out is all the information about this cone, okay? So I'm going to find everything because it does want us to find surface area and volume, so you know you're going to have to find every single piece of this cone. All right, so we already know the sides are 8. Here we go. Now, of course, I'm going to highlight, because I like to highlight, every cone and pyramid has a right triangle inside of it, right? So here's my right triangle. And, and I know that this is 4, which is the radius, right? Because it's half of the base of 8. And of course, this is a 30, 60, 90. So I also know that my height is 4 root 3. Or you can do Pythagorean theorem if you want to. I'll go ahead and throw the little 30, 60, 90s in just as a reminder. And yeah, I think that's pretty much everything we need, right? We've got all 3 sides of the right triangle, so we should be good. All right, so let's go find surface area. Okay. Oh, wait, hold on. Hold on, I was going to write all my information. Sorry. So it has a height of 4 oh my goodness gracious, a height of 4 root 3, a radius of 4, and a slant height of 8. All right, and that should be all the stuff we need. All right, sorry, here we go. So the surface area of a cone, right, so pi RL plus pi r squared, right, pi RL is our lateral, and then we have that 1 circle base, so pi r squared. So let's see, pi 4, 8 plus pi 4 squared. All right, looks like that's giving us 32 pi plus 16 pi. So it looks like we're getting 48 pi. And that's square centimeters for the surface area of that rotated cone. All right, and then we need volume. All right, so remember volume of a cone is 1/3 pi r squared h because 3 cones can fit in a cylinder. All right, so here we go. So 1/3 pi 4 squared 4 root 3. We don't need that height until we get to the volume. All right, so let's see. I'm just going to type all that in my calculator other than the pi. So 1/3 times 4 squared times, I'm just going to do 4. Oh, that's not a pretty number. Ooh, what a gross answer. Okay, this one's going to look really gross. Are you ready for this? So that's going to be 64 pi root 3 over 3. That darn 1/3. Now, how did I get that? Well, I can only multiply outside numbers. So in my calculator, I'm going to do 1/3 times 4 squared times 4. I can't touch that root 3, right? And when I type all that in my calculator, I get 64 thirds, right? And then in my numerator, I just need to make sure that I'm going back and putting the pi and the root 3 in. And the square root should be the last thing written. You shouldn't write anything after the root 3, right? He should be in the back. Okay? All right. And of course, that's cubic centimeters. All right. We're not used to seeing answers that have pi's and square roots in them, right? But in this case, we do. No big deal, as long as you get them all in your answer. Okay, we've got 2 left, right? So number 7, this one we are going to be working with a graph. It says the segment joining 0, 0, okay, 0, 0, and 3, 4. Okay, 3, 4. So the segment joining those two guys is rotated about the y-axis. So here's my axis of rotation, the y-axis. So we're taking this segment and we're spinning it around. Well, if you want to, you can go ahead and connect the segment to the y-axis, because in essence, when this point spins around, it's going to create a circular bottom, right? And we already know this. So if you want to go ahead and draw that in, you totally can. If you don't want to, that's okay too. Right, so if I take this vertex right here and I revolve it around the axis, we know it's going to be 3 units on the other side because it's a reflection buddy as it spins, and then voila, there's our cone. Right, so if I take a segment, a diagonal segment, right, and I spin it around an axis, right, we're going to get a cone shape. So I'm going to do what I've been doing this whole time. I'm going to go off to the side. Hey, it's a cone. And what do we know about this cone? Well, I know it has a radius of 3. I also know it has a height of 4. And I know I'm going to need that slant height, which of course is going to be 5, because it's a 3, 4, 5 Pythagorean triple in this right triangle that's being created inside the cone. Right, so radius of 3, height of 4, slant height of 5. All right, here we go. More surface area and volume. So I'm just going to run through these really quick. So remember the surface area of a cone, pi RL plus pi R squared. So just plugging our numbers in, pi 3, 5 plus pi 3 squared. So 15 pi plus 9 pi, so 24 pi. And I'm just going to put units squared because we're just on a coordinate plane with units. And there you go. And then, of course, volume of the cone is that 1/3 pi r squared h. So 1/3 pi 3 squared 4, right? So that's going to be 9. So what's that, 12 pi? And that would be cubic units. And voila. All right. And you probably know what's coming. On part B, it says, how would your answer change if you rotated the triangle bounded by the segments and the x-axis? All right, so same segment. So it's going from 0, 0 to 3, 4. Right, so here's our segment. But now we're rotating about the x-axis. Right, so now we're spinning this way. Okay, so I'm going to do what I've been doing the whole time. Right, I'm going to take that. I'm going to rotate my vertex. Oh, that wasn't a very good. Get this a little higher. Oh, he's a little off, but I'm just going to let that go. And then, of course, I'm going to connect this guy. So we still have a cone, right? That has not changed, right? And you'll notice that here's our little right triangle, right, inside of said cone. All right, and so I still have a cone, but it's a different shaped cone because we went the other way. So now all of our numbers are kind of flip-flopped, right? All right, so now my radius is 4. Now my height is 3, but of course my slant height is still going to be 5, right? Because that's still going to be the hypotenuse of our 3, 4, 5 triangle. All right, so how does this change things? Well, just like the cylinder one we did up top, right? If you have a different radius, the radius is being squared, so that's going to change everything. We have a much bigger base, right? Notice how much bigger the circle base is than on the other one. So it's definitely going to change our surface area. So pi RL plus pi R squared, plugging in our new numbers, pi 4, 5 plus pi 4 squared. Right, so this is going to give us 20 pi plus 16 pi. So I'm getting 36 pi square units as my surface area. So it's definitely bigger, right? Because it had a bigger circle. Again, it also had a bigger lateral area, right? Because of we were doing 4 times 5 instead of 3 times 5 with that slant height. All right, and then volume formula, 1/3 pi r squared h. So 1/3 pi, our radius is now 4, and our height is 3. Right, and so we're taking 1/3 of 3, 16 pi is what we should be getting there. And that's cubic units, right? And notice that's pretty significantly bigger, right? We started with 12 pi and it increased to a volume of 16 pi just by spinning it around a different axis. All right, I'm hoping these revolving solids, I hope all of that makes sense, right? If not, you can always come in for tutorials and I'd be more than happy to help you out. All right, you guys, see you soon.